Okay, so we continue. The other video was abruptly being stopped because a phone call came. So we were talking about the dice, right? So for n number of times which you put the dice, there will be 6 raised to n times. So similarly here, in the case where omega is being, when it is governed by the volume, for the first particle the full volume is available, right? For the second particle in the box, uh, again the full volume is available. Why? Because the particles are not interacting with each other. So which means that this particle is not seeing this particle at all at any point of time. So that is what the assumption implies. So for the second particle also the full volume is available. For the third particle also the full volume is available. So in terms of the volume, the total number of possibilities should be written as the product of the individual possibilities, right? So the first particle, the possibility is V, second it is V, third it is V again, and the fourth it is V again, and so on and so forth. So therefore, the total number of particles for the total n number of particles is written as V into V into V into V into, and so that it is V raised to n. And we have the FV. Now, of course, I can write yes in terms of omega, right? S is equal to K ln omega. I can write it as S is nearly equal to K n K ln V plus K ln Fe, right? So that is one way of writing it. Anyway, let's continue. Now, our idea should be to calculate the value of Fe. So, how to calculate the value of Fe? Now, what is the idea which you know about the ideal gas, right? So, we know that if we have one single particle confined in a box, we know the energy, how it is being, what is the energy of that particle. So that is the case of particle in a box. And what is the expression for energy? E is equal to h squared by 8 ml squared into n squared. N is the quantum number. Here we have a three-dimensional box, so I can write E of nx, ny, nz is equal to nx squared plus ny squared plus nz squared. Yeah, this is 24, this is 25, yes, and this is 26. So E of nx, ny, nz is equal to h squared by 8 ml squared, nx squared plus ny squared plus nz squared. Now, you might okay, you will ask me the doubt connected to this one in the class. Then only I will clarify that point over there. I just want to make sure that you people are really thinking over it. Yeah? So that is it. And now what can we do? Now we should be extending this to all the particles, n number of particles in our system, right? So let this stay over there. So therefore, if I need to extend it for n number of particles, let me take one of the particle as ith particle, right? So I can write E of nxi n by I nzi. But one of the strong points which we should be telling now is that I am assuming that they are classical particles, so therefore they are identical and they are distinguishable. Hmm? Um, identical. All particles are identical and they are distinguishable, because I am telling that they are essentially this one, right? They are essentially classical particles. So identical and distinguishable. So the total energy E can be written as sum over I equal to 1 to n EI is equal to h squared by 8 ml squared, sum over 1 I is equal to 1 to n nx squared plus ny squared plus nz squared, right? Which I can simplify, and let this be question number 27, and this can be simplified as h squared by 8 ml squared sum over I equal to 1 to 3n nr squared. This is 8. So h squared by 8 ml squared I is equal to 1 to 3n nr squared, where r is the r is x, y or z, whatever. Okay. Now we need to calculate the omega for the system, right? How to do that? Still we are long way off, but this equation in a way gives us an idea. How? This suggests that if I have a system where let me try to explain this to you. This is may not be really be applicable every time, but still for this case. So if I have nx scale like this or here, so if it is a one-dimensional system, instead of a box, if it is a one-dimensional, if the electron was restricted to move, the particle was restricted to move in the only in the x-axis, I can name it as say 0, 1, 2, 3, 4, 5, 6, and so therefore this distribution, the distribution in which this each of the microstates will come through in the energy area or in the energy situation will be governed by these values 0, 1, 2, 3. So if the particle goes to 1, that becomes 1 microstate. Instead, the same particle goes to 2, that becomes a second microstate. If it 3, second, the third one, 4. So similarly, right? So if it was a one-dimensional moving case, this will be the value. So basically, this energy is being governed by some kind of a distance between in the nx sphere, in the nx line. So similarly, if you have something like this, ny, 1, 2, 3, 4, 5, etc. So if this particle was allowed to move in a two-dimensional surface, again that will be governed by my movement in the y or in the x. So in the x space it can move maximum to the 6. In the y space it can move into the maximum to the 6 over here, right? This is just another representation. So imagine that, remember that this is all in the theoretical way. So my drawings may not be extendable to each and every case. This is just for your understanding of the situation, which I'm using this. So this expression can be now be represented with some kind of a arc like this, where the particle is being governed by some kind of a radius. If it was a circle, it will be governed by some kind of a circle. It is the movement or the microstate, the origin of the microstate in terms of its energy is now being limited by a limiting value of the nx and the ny. So what one would like to tell or make a similarity, basically the so-called nr is similar to our radius of the system. So if I imagine that energy, the volume in which this particle is allowed to move, this nx value and the energy sphere, the region which generates the microstates can be assumed to be similar to a sphere with radius nr. So that is the best explanation I can give it to you in terms of how to calculate the microstates in terms of this expression. You can definitely look into Patria for his way of communicating this point. So naturally all my cubes in this sphere, the so-called energy sphere, will be unit cubes. So if I need to calculate the number of microstates, now I have an easy way of doing it. I need to just count the total number of cubes in the system. So what is the total number of cubes in the system will give me the total number of microstates possible, right? Because these are the maximum possibilities in which this system can move. This is the maximum sphere in which it can move. And each of the cube in the system, the particle being in each of this cube will give you another microstate. Therefore, since this is a unit volume cubes, which I am assuming, if I count the total number of cubes in this sphere, naturally I will get the total number of microstates. Okay, so I should write each cube in the figure will represent a microstate. And so now my idea is to count the number of cubes. Total volume, total unit volume, total number of unit volume cubes will give me omega. So that is the idea in which we will be. So in the next video, our idea will be to calculate the total number of cubes in this volume, or basically we should be able to calculate the volume of the sphere, because now right? If I tell that I have a box which is divided into 6 cubes and its total volume is 6, then what is the individual volume? The individual volume of each cube? It is 1, right? So similarly, now I am assuming a sphere which is having all the cubes which are of unit volume. So if I know the volume, that will be equal to the total number of microstates. So the volume will give me the omega. So our idea should be to calculate the total volume of the sphere, which we will do in the next video.